Welcome to Energy Session 12.0, Lighting Practices. This EMSI training section covers energy basics on lighting practices. Your presenter is Rick Mitchell. Here we'll apply the theory from the previous section to practical situations. This module will give you an understanding of energy use in lighting in the residential, business, and commercial sectors. Lighting is an essential service in all industries, and good lighting serves many useful purposes by illuminating an area so that tasks may be carried out safely, as well as improving mood and productivity. We'll cover lighting application across technologies and the efficiency and power consumption associated with these technologies. Light technologies. First, we'll look at current lighting technologies, including types of lamps and control methods, as well as the advantages and disadvantages of each technology. It is important to identify the key characteristics of these technologies in terms of lighting, quality, and energy use in order to understand how to apply them in different situations. A lamp is any equipment which produces light. In lamps, there are four main ways that light can be produced from electricity. 1. Incandescence, which is the production of light from heat. Electricity is used to raise the temperature of the filament until it is incandescent. 2. Electrical discharge, which is the production of light from the movement of electricity through a gas or vapor. In lamps using this principle, the atoms of the gas get excited or agitated, and this produces light and sometimes ultraviolet and infrared energy. 3. Phosphorescence and fluorescence, which are the processes of converting invisible ultraviolet energy emitted normally from an electrical discharge into visible light. Materials called phosphors cause UV energy to make this transition into visible light. The fourth and final way employs the induction principle, which is the same process as the fluorescent lamp. However, induction lamps do not use electrodes. They use a high-frequency generator with a power coupler to produce a radio signal frequency magnetic field to excite the gas inside the space. There are a few categories of lamps which more generally fall under the categories of incandescent, LED, or gas discharge types. From this hierarchy chart, you can see that gas discharge lamps are the most numerous in variety, though these are more usually found in industrial applications. In this section, we will be discussing the common types of technologies available to produce light. These include the incandescent lamps, fluorescent lamps, high-intensity discharge lamps, light-emitting diodes, as well as some additional lighting types available in industry. The incandescent lamp, or the common light bulb, is still the most common form of lighting. In an incandescent lamp, light is emitted when electricity flows through and heats a tungsten filament. In this process, most of the energy generated is thermal energy. The main parts of an incandescent lamp, also known as GLS, or general lighting service, include the filament, the bulb, the fill gas, and the cap. As mentioned, this lamp is a fairly simple technology that involves current passing through a tungsten filament of high resistance, raising its temperature so it becomes incandescent and emitting light and heat. The outer glass bulb is usually filled with amounts of argon and nitrogen to inhibit the evaporation of tungsten and arcing across the filament. The bulb is usually clear or has a pearl finish. The incandescent lamp has an excellent CRI and a warm color temperature, which provides brilliant color rendition of human skin tones. Though due to the fact that most of the electricity they consume is lost as heat, they have a very low lumen per watt performance. They also have a poor lamp life of about 1,000 hours. In 2009, the Australian government introduced a law that restricted the importation of inefficient incandescent general lighting service lamps after recognizing how inefficient they were compared to the other affordable technologies on the market. It should be noted here that variations in the supply voltage from the rated lamp voltage can dramatically affect the performance of an incandescent lamp. In this figure, we can see that as the voltage increases from the rated voltage, the life of the lamp takes a sharp decline. For instance, a 10% increase in the rated voltage can see the life of the lamp reduced by over 60%. This voltage increase does come with an increase in the lumen output of the lamp. However, the large drop in the life of the lamp means that it is desirable to maintain the rated voltage. A small drop in supply voltage would see a steep increase in lamp life. However, the lumen output would decrease steadily as well. Until more recently, incandescent lamps were commonly used in households and buildings, generally used in areas where lighting was seldom used or lighting was used for short periods of time, such as laundries and toilets. One major problem with incandescent lamps is the evaporation of the filament material. This is caused when the high temperature evaporates the material, thinning the filament, deteriorating the material and reducing its lifespan. A break in a filament in a gas-filled bulb causes the bulb to draw heavier current, increasing the energy consumption of the bulb. Here is a quick comparison of the advantages and disadvantages of the incandescent lamp. Some advantages are that they turn on immediately, and they require no extra equipment. The well-known pear-shaped light bulb was inexpensive to buy but costly to run, as it consumed so much electrical energy as heat, with only 5% of the electrical energy being converted to visible light. That is why these lamps have already been phased out. This is referred to as luminous efficacy, which is the lumens per watt output by a lamp. We can see from this diagram that the incandescent lamps are very poor in this area. Essentially, a 100 watt incandescent lamp produces about the same amount of lumens as a 20 watt fluorescent lamp, highlighting its inefficiency. In fluorescent tubes, a small amount of mercury mixes with inert gas to conduct the electrical current. The excited gas gives off invisible UV light, which then excites the phosphor coating on the glass tube, which causes the phosphor to emit visible light. Fluorescent lamps vary in color temperature from warm to cool according to their phosphor coating and usually have a very good CRI. Typical lamps have a high LPW performance, however they are only designed for the lower range of the lumen output scale. They have a moderate lamp life that can last up to 15,000 hours. They are made to standard thickness, namely T12, T8, T5, and T2, where the number after the T represents the thickness of the lamp in eighths of an inch. So a T8 lamp is 1 inch thick. These lamps are not designed to operate directly from main supply and therefore require some extra equipment to control the amount of electrical power coming through. Fluorescent tube lamps require a higher voltage to initiate discharge and then require another device to control the current. Fluorescent lamps cannot control the current on their own, as drawing high currents from main supply can damage the lamp. In order to prevent damage, they are equipped with a set of conventional control gear. This gear usually includes a ballast, which controls the amount of current going through the lamp, a starter, which is a switch that starts the lamp, and a capacitor, the component that corrects the power factor. There are also electronic ballasts available. These are much more efficient as they produce less heat and also run the lamp more efficiently. Conventional ballasts contain large magnetic cores, making them heavy and bulky. Electronic ballasts are much more compact and lightweight. The figure shows the spectrum of light output of a typical cool white fluorescent lamp. Notice the large peak in the blue, which causes the light to appear cool. Compact fluorescent lamps are a smaller version of the fluorescent tube and are designed to replace incandescent GLS lamps. These compact fluorescent lamps are electronically ballasted to improve efficiency. CFLs vary in color temperature from warm to cool according to their phosphor coating and usually have a good CRI. Typical lamps have a moderate LPW performance and they have a moderate lamp life that can last up to 10,000 hours. The table shows the power ratings of the CFL equivalent to incandescent lamps with similar light output. There are two types of compact fluorescent lamps, pin-based and integral ballast. As the name suggests, the control gear is housed within the lamp base. The advantage of fluorescent lamps is that they are economical to operate, have a large color range, and they have a much cooler operation which reduces cooling load. They are long-lasting and provide a soft light. The disadvantages of fluorescent lamps are that they can be expensive to purchase, often require a ballast and starter, will flicker on startup if using an iron ballast, and are slow to reach full brightness. It is likely that CFLs will remain for the short term, however there are still more efficient technologies entering the market. LEDs are likely to take their place in most settings in the future. High-intensity discharge lamps, or HID lamps, are a type of electrical lamp that produces light by means of an electrical arc between tungsten electrodes. The electrodes are inside a translucent or transparent fused quartz or fused alumina arc tube filled with nitrogen and gas and metal salts. This gas assists the arc's initial strike. Once the arc is started, the metal salts are heated and evaporate, forming a plasma which intensifies the light produced by the arc and reduces its power consumption. It is the same principle as lightning, where the high voltage that builds up in the storm clouds discharges itself through to the ground. The passage of electrical current through the atmosphere excites the nitrogen atoms to give out a bluish-white light during that split second of the discharge. HID lamps are typically economical to operate and are often found in high bay and wall-mounted bulkhead and floodlight type fittings. A disadvantage of HID lamps is that there is a time delay before the lamp reaches its full light output, and they also need to cool down before they can be restruck, which can present a safety issue if the power cuts out momentarily, as the lights will not turn back on instantly. As HID lamps generate intense light, they are ideal for large areas with high ceilings over 15 feet or outdoor spaces such as sport fields and parking lots. These lamps are also great for lighting large spaces such as warehouses, service stations, and large commercial areas. They are usually very economical to operate, however they are expensive to install and require control gear for operation. There are a few types of HID lamps, and depending on the lamp, they produce different characteristics. Some have higher light intensity and correlated color temperature, whilst others boast high CRI, life expectancy, and efficiency. Metal halide lamps are common and used when normal color appearance is required, such as television production. Mercury vapor HID are not as common now as metal halide. HID lamps have been the technology of choice for high light output applications for many years. However, with the advancement of technologies such as LED and induction lamps, HID lamps could see a decline in use in the future. The older type of HID lamps are the mercury vapor lamps. In this type, the light is generated by exciting mercury atoms in the electrical discharge in argon gas. The argon gas conducts the electricity between the tungsten electrodes in the quartz arc tube. The internal pressure of the tube is nearly 3 times the atmospheric pressure and are usually called high-pressure mercury lamps. At these pressures, the mercury atoms can create most of the colors of the visible spectrum, hence why the light produced has a blue-green tint. Mercury vapor lamps also use control gear, which chiefly involves a ballast which controls the current entering the lamp. They do not require a voltage igniter as they start at 170 volts, which is within the main supply voltage peak. There are also self-ballast models available. Like incandescent lamps, mercury vapor lamps are currently being phased out as they are not very efficient and have a high mercury content. They also have poor CRI values and low efficacy compared to the rest of the HID lamp range. Their lifespan ranges from 15,000 to 24,000 hours, and these lamps are used mainly in industrial lighting, sign illumination, and stadiums. As previously noted, the CRI of mercury vapor lamps is quite poor. This can be seen on the spectrum intensity figure shown below, with peaks in the yellow and green wavelengths. The metal halide lamp is very similar to the mercury vapor lamp, but they have an additional metal halide in the mercury discharge tube which provides a greater spectral output and produces greater quality white light. Using a ceramic material in the discharge tube also improves the performance of the lamp. Metal halide lamps also operate at a high pressure, where the different metals are excited to create the light. Control gear is also used with metal halide lamps, with electronic control gear used mainly for lower wattage metal halide lamps up to 150 watts. These lightweight devices ignite the lamp and operate them at their optimal performance. Metal halide lamps have the best luminous efficacy out of all the HID lamps and have an average lifespan that ranges from 6,000 to 24,000 hours. The high-pressure sodium lamps use a sodium-mercury alloy called sodium amalgam in a discharge with xenon gas and operate a much higher temperature than other HID lamps. The sodium creates an orange light and the mercury produces a red and blue light, therefore producing a white light with an orange tint, as shown in the spectral intensity figure. The small arc tube is made from a ceramic material which is resistant to the molten sodium. High-pressure sodium lamps require a voltage igniter as they need between 3,000 and 4,500 volts to start the lamp. Some igniters are installed inside the outer bulb and a ballast is also required to control the current. Some applications of high-pressure sodium lamps include road and street lighting, public areas or parking lots, cold storage lighting, or cold ambient areas, and also flood lighting of buildings. Low-pressure sodium lamps operate on the same principle as its high-pressure counterpart. They generate light by exciting sodium metal in the discharge in a combination of neon and argon gas space at a low pressure. These lamps are the most luminous efficient of all the high-intensity discharge lamps. Due to the corrosion potential of molten sodium, a special sodium-resistant glass has to be used for the arc tube instead of quartz or normal glass. Similar to the other HID lamps, they require a ballast to control the current, as well as a high voltage to ignite the lamp. In general, low-pressure sodium lamps have poor color rendering due to their distinctive deep orange light. However, due to their high luminous efficacy, they are widely used in applications where high efficiency is favored over color reproduction, such as car parks and street lighting. Their lifespan is approximately 16,000 hours. Light-emitting diodes, more commonly known as LEDs, are a semiconductor device that emits infrared or visible light when charged by an electric current. They operate by electroluminescence, where the emission of photons is caused by the electronic excitation of a material. The materials commonly used are gallium arsenide, aluminium gallium arsenide, or aluminium gallium indium phosphide. Depending on the material, the diode will produce a different color. For example, red LEDs generally use gallium, aluminium, and arsenide mixtures. Orange and yellow LEDs most often use gallium, aluminium, and either indium or phosphorus, and green and blue LEDs typically use either silicon and carbon or gallium and nitrogen. LEDs are compact in size and are used in small spaces and applications. LED retrofits have been designed to replace most common lamps. One disadvantage of LEDs is that they are very directional, so the fittings in the lamps must be strategically designed to achieve an evenly distributed light. LED retrofits are not necessarily the best solution and should be assessed and used on an individual basis. Current replacement LEDs use at least 75% less energy and last 25 times longer than incandescent lighting. They are very directional, making them a perfect match for downlights and task lighting. They also produce very little heat compared to other types of lamps, however they still require a good heat sink if they are to last for the rated lifetime. It is important to ensure that LEDs are compatible with the existing ballast or transformer before installation. It should be noted that LEDs are not normally given a CRI rating, as they perform poorly on this scale, even though they provide good quality light. The lighting industry is looking to introduce a new standard for rating the color rendering of lamps, along with introducing better industry standards and regulations on the quality of LED lamps. When purchasing LEDs, be careful to check the specifications given by the manufacturer, as they can sometimes be misleading. For instance, they may quote the instantaneous light output instead of the average light output. The instantaneous output is often only achieved for a few milliseconds on startup, whereas the average output is the maintained lumens. Some applications of LED lamps or lights include traffic signals, conventional or general lighting, and street lighting. LED lamps are a fast-growing technology, however they still require further improvement in heat dissipation and light distribution engineering before they will be adopted as the new standard technology. Government regulation and a drop in the price of LED lamps will help move the technology forward. Induction lamps are a different type of fluorescent light. They work by inducing a current flow through a tube by way of an electromagnetic field generated by carefully shaped coils around the outside of the tube. These work similarly to fluorescent lamps, however the process in which they excite the mercury is the difference. Induction lamps do not use electrodes, which usually fail after 15,000 to 20,000 hours, allowing them to last up to 100,000 hours. These lamps turn on instantly, which makes them perfect for installation with sensor equipment or in applications where it is necessary that the lamp turns on as soon as the switch is on. For example, a tunnel. Induction lamps usually have a cool color temperature and a high CRI rating, and also a high efficacy. These lamps are very popular as they are economical to operate and have an extremely long life. Induction lamps are often used for large space lighting or high ceiling applications where normal lamps are difficult or dangerous to access. They also operate well in both hot or cold conditions. Halogen lamps are categorized as an incandescent lamp. They also have a tungsten filament which is encased inside a quartz casing filled with halogen gas. This gas combines with the tungsten vapor at high temperatures, and then the gas will redeposit the tungsten atoms back into the filament. This recycling process extends the life of the filament and therefore the lamp. They are also more efficient than the regular incandescent lamps. The halogen lamp has an excellent CRI and a warm color temperature. They have a very low LPW performance, as most of the electricity they consume is lost as heat. They have a moderate lamp life that ranges from 2,000 up to 10,000 hours. These lamps have a variety of applications, from common household use to buildings and office spaces to display lighting. Neon tubes are a glass lamp that can be molded to a required shape and designed to produce numerous colors depending on the phosphor coating on the tube. They operate in a similar fashion to fluorescent lamps, except that they use a cold cathode which eliminates the need for a starter or ballast. All that is required is a transformer to increase the voltage and limit the current to 25 to 100 milliamps depending on the application. Neon lamps come in a range of color temperatures, offer a medium lumen per watt performance depending on the choice of color, and have a lifetime of up to 50,000 hours. They are used for signage and indirect lighting such as ceilings. Fiber optic lighting is used for feature lighting such as the case shown in this image where the roof has been transformed to look like the night sky. An LED driver is used to direct the light down the optical fibers. Solar lamps usually come as a self-contained unit, which is basically comprised of a solar photovoltaic panel, rechargeable battery, and LED or fluorescent light. They range from smaller garden lights to street lights and are extremely advantageous in situations where grid power has not been run to the light. Natural light is far superior to artificial light. It has been proven in many studies around the world that natural light increases productivity and the general mood of workers and customers. It is by far the most energy efficient lighting option, especially for warehouses that have large areas with open spaces. Some designs include skylights, light shelves, atriums, and windows. A skylight is any window installed in a roof and is simply designed to allow sunlight to light an internal space and is much more effective than a typical window in a wall. Ideal design standards suggest a skylight area of 4 to 8% of floor space, depending on climate conditions, latitude, and skylight characteristics. Light shelves extend out from a window into the inside space. The sunlight entering from the window hits the shelf and is reflected into the internal space, providing a natural, evenly distributed light. Atriums allow workers to escape the office and enjoy an open area with natural lighting and fresh air. The atmosphere has been proven to boost the morale of workers. These spaces can be an efficient and novel way to bring light into deep planned buildings. Common lamp connection types include the GU10 and MR16, which are often seen on halogen downlights, the B22 bayonet connection, and the E27 Edison screw connection. Luminaires and control gear. This section will look into the luminaires and control gear that are used with lighting and lamp installations. Safety of lighting and ingress protection will also be discussed. Ballasts are devices used to limit and regulate the current entering a lamp, not only to initiate operation but also to protect it. They are mainly used in fluorescent lights where they also help regulate the flickering of the light and in high-intensity discharge lamps. There are three main types of ballasts available. Magnetic, which are the least efficient and no longer available in Australia. Electronic, which modify the frequency of power in accordance with the needs of the bulb. These are the most efficient type of ballast and also the most expensive. And a hybrid ballast, which is a combination of magnetic and electronic technologies from both magnetic and electronic ballasts. These are more efficient than magnetic but less than electronic. Ballasts for fluorescent lamps rated between 15 watts and 70 watts fall under the MEPS requirements. Adding controls to a lighting system can improve efficiency. Control equipment includes switches, dimmers, sensors, or timers, or in a combination of any of these, and can be independently installed to regulate the amount of light produced and consumed in a space. Switching. A manual switch is usually found on a wall near the entry to a room or building. However, this is not always the case. It is the simplest form of controlling lights and requires the occupant to physically turn the lights on or off when they enter or leave. Due to this nature, the usage patterns of the lights can be difficult to predict, as each occupant may place different importance on whether the light is left on while the room is unoccupied. A daylight switch is a device that switches a circuit on or off whenever it senses that the illuminance has passed a certain threshold. For example, the device could be designed to switch the circuit off during the day while there is light, and then turn the circuit on when it is dusk and the light falls below a defined threshold, typically around 100 lux. This is useful for when lights are used externally and only need to operate at night time when it's dark. Typically, the photo sensor is mounted on a roof or the side of a wall, separately from the switching device that is mounted in the switchboard. There is also the option on some models to have a bypass switch so that the circuit can be turned on or off for testing and maintenance. Manual or remote dimmers are an excellent way of using energy-efficient measures to retrofit existing technology while using minimal rewiring. This can be used to keep illuminance levels constant when natural light is made use of. As the daylight becomes brighter in the room, lights can be automatically dimmed using electronic controls to maintain a constant level of illuminance. Some types of lighting, including fluorescent and HID lamps, require compatible ballasts and controls to use the dimming feature. Depending on the device of choice and the usage of its dimming features, the payback period can range from short to extensive. Motion sensors are widely used in home security devices but can also play an important role in lighting technologies. Rather than requiring occupants to manually dim or turn off lights, the sensor will automatically perform the function and save energy in the process. Photosensors adjust the light according to the ambient light and will work even when occupants are within the range of the sensory device. Some are programmable to dim to a prescribed lumen rating, while others simply turn the lights off if an adequate level of light is present, either through windows or adjacent lighting features. Timers vary from highly sophisticated computer-controlled systems to simply manual dialed clocks, yet both types can have a calculated effect on energy savings when used in areas where the lights typically remain on full time. They are used where lighting is only required for a set time in the day or week, such as in a regular office or car park. High-quality timers contain a small rechargeable battery so that they can retain the same time settings in the event of a power outage. Luminaires or fixtures are the physical units that house the lamp and distribute light or direct the light in different ways. They also serve to protect the lamp from the environment depending on the application. Other electrical components of a luminaire include the lamp holder, power supply terminals, and associated wiring. These components must be appropriate for the insulation class and extra low voltage fault protection. Some luminaires require a heat sink to allow heat to be dissipated from the lamp. This heat sink should be open to the air and not covered, otherwise the lamp will overheat as the heat will be trapped. Usually, the way you distribute light must be assessed on an individual case, as the same fixture is not always appropriate for all situations. The types of fixtures or luminaires are direct, direct-indirect, indirect, and shielded. Direct fixtures distribute 90 to 100% of the light downward. This type of lighting can create shadow and glare issues when not installed appropriately or with suitable fixtures. This is the most common form of lighting in both residential and commercial applications. Direct-indirect fixtures distribute light equally, both upwards and downwards, and use surface reflectance to aid in light distribution. This can reduce direct glare as little light is emitted horizontally. Indirect fixtures distribute 90 to 100% of the light upward. It is always important to ensure that the upper walls of the room, as well as the ceiling, are clean and of a reflective nature to permit the light to reach the area or space. This type of fixture can provide the most illumination and also the least amount of direct glare. They are mainly used in offices. Shielded fixtures are usually accompanied by a diffuser, louvers, and lenses to cover the lamp. With these components, they prevent glare and distribute the light more evenly or in a specific direction as necessary. Diffusers are usually made of a translucent or semi-transparent material, generally glass or plastic. They are installed on the bottom or the sides of light fixtures to control the brightness. The lens design also features prisms and flutes to distribute light in specific ways. The louvers are baffles that shield the lamp from view and also reflect light. The louvers can be modified to control light and decrease brightness. A refractor provides precise light distribution by redirecting light rays using prisms or other shapes. A reflector redirects light from a lamp via reflection, ideally in a useful direction. A diffuser is a translucent material that shields the lamp and randomly redirects and scatters the light and also reduces glare. There are two main types of light sources, linear and point sources. With a linear source, light is emitted from a line or linear origin and usually has a cylindrical type distribution, whereas a point source causes light to be emitted from a single point and usually has a spherical distribution. The graphs show the polar luminance distribution curves for a recessed fluorescent luminaires. This gives an indication of how the light is distributed at different angles. The amount of lumens radiated at different angles from the luminaire can be determined by following a particular angle line out from the center until you reach the curve. This will give the lumens for that angle. The vertical angles can be measured at different horizontal angles as shown in the figure on the right, and these different curves can be drawn on the same graph near the left. The light output ratio of a luminaire is the ratio of light emitted from a luminaire to the light emitted from the lamp. This is broken down into upward LOR and downward LOR based on whether the light is emitted above or below the horizontal plane. The example here shows the difference in light output between an open twin fluorescent luminaire and a twin fluorescent luminaire with a reflector and louvers. You can see that the reflector prevents any light from being directed upwards and directs an extra 5% of light downwards. This design means that more light is directed where it is useful and also provides some protection of the lamps. There are many different methods for mounting luminaires. These methods include recessed and semi-recessed, ceiling mounted, suspended, track mounted, wall mounted, and wall recessed. The recessed and semi-recessed family of luminaires is large and diverse. Recessed luminaires are direct in distribution, whereas semi-recessed can offer the opportunity to incorporate an indirect component. Types of lighting within the recessed and semi-recessed family include linear general, which involves a linear light source that provides a general light distribution. The example here is fully recessed and therefore only directs light downward. Point general, which involves a point light source that provides a general light distribution. The example here is also fully recessed, only directs light in a downward direction. Linear wall wash, which involves a linear light source that provides a wash of light aimed at a wall. The example here is fully recessed. Point wall wash, which involves a point light source that provides a wash of light aimed at a wall. The example here is also fully recessed. And point adjustable accent, which involves a point light source that provides a wash of light aimed at a wall. The aim of the luminaire can be adjusted in the recessed luminaire. Many types of luminaires are available in ceiling mounted versions and offer the designer the ability to provide a decorative element or overcome a non-accessible ceiling space. Ceiling mounted varieties can provide general illumination as in an office environment or maybe a single monopoint track head illuminating a picture on a wall. Linear general involves a linear light source that provides a general light distribution. Open fluorescence directs some light upward, but if you add reflectors and louvers, you can direct that light downwards where it is more useful. Point general involves a point light source that provides a general light distribution. The example here is an open HID high bay with a metal reflector that only directs light in a downward direction. Suspended or pendant lighting involves the luminaire being attached to a chain or wire which is attached to the ceiling. This allows the luminaire to be mounted horizontally where the ceiling is at an angle, allows the light to be brought closer to where the task is, and also allows the use of indirect lighting to illuminate a space. These figures show some linear general luminaires making use of indirect and direct lighting. Point general suspended lights make use of a single point source to provide a general light distribution, either directly or indirectly as shown in these figures. Track-mounted luminaires offer flexibility of lamp types, distribution types, aiming angles, and positioning. Tracks are easy to apply and can cost less to install than fixed units due to a single power point for any row of possible luminaire locations. Track-mounted luminaires include linear wall wash, where a linear light source provides a wash of light aimed at a wall, and point adjustable accent, where a point light source provides a wash of light aimed at a wall, such as the LED luminaire shown in the top figure. These types of luminaires can be manually aimed after installation. Wall-mounted luminaires help balance the vertical brightness of interior walls and patterns of visual interest, or add a luminous style element which may not provide functional illuminance at all. Wall-mounted luminaires must consider mounting distance from the ceiling, light distribution, and viewing angle for glare control. The example of the linear general light here provides general uplight from an alcove in the wall using a linear light source such as a fluorescent or neon lamp. The point general light shown in this figure provides general uplight using a wall-mounted linear light source such as a metal halide or halogen lamp. Note the distribution is designed to light the wall and a large area of the ceiling. A steplight is used to specifically light a stairway, usually for safety reasons. Note that the light distribution is directly completely downwards so that there is no glare shining in a person's eyes as they are climbing or descending the stairs. Pole-mounted luminaires are used to light areas such as roadways, footpaths, courtyards, parks, fields, and car parks. The poles can take on a range of heights and spacing depending on the required illuminance and generally distribute the light in a wide downward beam using reflectors. Task lamps are designed to light a specific task area such as a desk without having to light the whole space to the required working illuminance. For example, a desk could be lit to 300 lux using a desk lamp, while surrounding areas could be generally lit by ceiling-mounted fluorescence to 100 lux. Germicidal lamps produce UV light and small amount of visible light. They are used for water disinfection and should be shielded to prevent direct or reflected waves reaching the eye as they can cause damage to the retina. Agricultural or hydroponic lamps are used to provide the light needed to grow plants indoors. Historically, fluorescent tubes were used for this application, however they were replaced by HID lamps because of their increased efficiency. Typically, metal halide lamps are used for their high output of blue light. LED lamps have recently been developed to suit this application and consume much less energy. However, they are still quite expensive compared to HID. This table comes from Australian Standard 1680.1 and outlines recommended maintained illuminances for interior areas. This is important if you are making recommendations on lighting initiatives in high-performance areas where safety is an issue. This table shows the recommended color temperatures for different applications. Domestic and hospitality settings usually have a warm light to create a more relaxed mood. Retail ranges from warm to very cool light and is usually around the 6000 K mark in order to give similar illumination to that of daylight. This allows customers to view the color of products roughly how they would appear under sunlight. All equipment nowadays goes through a stringent safety review. Depending on the type of environment where the lamps will be installed, the type of enclosure and ingress protection will differ. Ingress protection ratings are standards for the electrical enclosure of electrical equipment. They provide environmental protection to the equipment, or in this case, the lamp. The ratings refer to protection against solid material and liquids entering the enclosure that houses the electrical wires or other components that are vital to the performance of the lamp or equipment. IP ratings are not necessarily required for household installations, only in hazardous areas or areas where environmental conditions may reduce the running efficiency or lifespan of the lamp. A hazardous area is a space in which the atmosphere contains or has the potential to contain a sufficient quantity of flammable or explosive gases, dusts, or vapor. Some examples of these are fuel terminals, service stations, or even paint warehouses where decanting occurs. There are many types of hazardous areas, and they too have their own classification. Specialized equipment for this type of workplace can only be installed and audited by an approved hazardous area qualified electrician or inspector. Here is a brief table depicting the type of IP rating that you can find on enclosures. They are represented by two numbers, the first number referring to protection against solids or dust, and the second number against liquids. For instance, a luminaire designed to be used outside, such as a street light, should be rated IP65 or IP66. Power consumption and efficiency. The total power consumption of a lamp can be easily calculated by multiplying the rated power by its respective time of use. In this case, the efficiency of the luminaire can be assumed as 1. Here the rated power is a measure of the power rating of the lamp and the ballast combined. Now let's look at reducing the power consumption of a lamp. The power consumption is essentially influenced by lamp technology, the type of ballast, and the lighting design. This image shows how to identify the power rating of a lamp. It should usually be written on the glass of the lamp, however some lamp types have the details written on the base. The lamp type can greatly influence the power consumption of the lighting system. Assesses each case individually. However, usually halogen downlights can be replaced with LED, incandescent lamps can be replaced with CFLs or LEDs, and HID can be replaced with induction or LED. Lamps should be chosen based on their suitability to the application, which includes aspects such as color temperature, luminous intensity, lamp life, and CRI. If a conventional magnetic ballast is used in the installation, these can be replaced with a lighter, more compact, and more energy efficient electronic ballast. The power consumption of a lighting system can also be reduced by using good design techniques. If there is a request for a higher illumination, make sure that the space has good quality of light before upgrading. Users can often request a brighter light when the space really just needs a task light or a reduction in glare. If the area is overlit, there is opportunity of delamping. This just means that the lamps are removed so that the correct illuminance is achieved. For instance, a triple lamp fluorescent fitting could have one lamp removed. Skylights could also be installed to reduce the power of the lamps required. Irrespective of whether you are designing a lobby for a 6-star hotel, an office, or an industrial facility, lighting design must take a holistic approach that not only provides efficient illumination, but creates a comfortable, stimulating, and interesting environment. Simply achieving the required illuminance does not guarantee a satisfactory lighting installation, and over-illumination will not necessarily act as a safety margin. Other aspects of the visual environment such as glare, contrast, and user satisfaction will have a greater impact on whether a lighting installation is perceived to be successful. Efficiencies in lighting are generally negligible and are often assumed to be equal to 1. However, maintenance of lights and passive lighting technologies can in many cases reduce the need for additional lighting. The proper upkeep of lighting fixtures, lamps, and luminaires won't necessarily improve the energy efficiency of the lighting system, but it will improve light levels, which may mitigate the need for additional lighting. Dust and dirt can build up on fittings, reducing the amount of quality of light coming from a fixture. The same is true for passive lighting technologies like skylights and light shelves. Increased light levels or increasing light levels back to the designed output will also make performing tasks easier and aid in providing a healthy and comfortable workplace or home. In order to reduce the time of use, the customer can manually switch the lights off when not used, or controls can be installed with appropriate motion sensors. Natural lighting combined with daylight sensors can also reduce time of use. The correct installation of manual switches in strategic locations, such as room entries and exits, means that lights are more likely to be switched off when not in use. Further time of use savings can be through the use of timers, daylight switches for external lights, motion sensors, photo sensors, and dimmers. Natural lighting can be capitalized on if skylights, light shelves, or windows are installed. Natural lighting will usually only influence time of use if implemented with photosensor controls that turn the lights off when the room reaches a specified illuminance. Combining lighting types is also another way of ensuring that task-specific activities can be undertaken in areas for general use. For instance, using a combination of indirect fluorescent lamps as general lighting, interspaced with LED downlights above desk spaces to improve direct light levels. An example scenario for lighting practices. Question 1. An old office currently has 20 x 36 watt T8 double fluorescent fixtures with heavy conventional ballasts, 12 watt per fixtures. The office runs 9 AM to 5 PM on weekdays, 50 weeks per year, and the employees switch the lights off when they leave. The office has changed from a drawing office to a regular administration office. The illuminance levels are still at 800 lux. You calculate that you can replace the double fixtures with 20 single 29 watt T5 high performance fixtures with 2 watt electronic ballasts to reduce the light levels to roughly 320 lux. However, the client wishes to trial the lower levels by delamping the existing fixtures to only have one lamp in each for 6 months, and then progress with retrofitting with the T5 fixtures after the trial. Calculate the energy savings after 2 years if the trial is successful and the T5 fixtures are installed at 6 months. The first stage is to calculate business as usual energy use of the current fixtures over a period of 2 years. This is the quantity of fixtures multiplied by the power of the fixture, which includes the lamp power and ballast power ratings, then converted from watts to kilowatts, and all multiplied by the time of use in hours. The current situation values are entered into the formula including the 36 watts per lamp and 12 watt ballasts per fixture. This equates to a business as usual energy use of 6,720 kilowatt hours for the 2-year period. The second stage is to calculate the proposed situation energy use, which includes the energy used during the 6-month trial and the energy used for the first year and a half of the retrofit. Using the same formula as the previous stage, substitute the known figures in the formula, this time accounting for just one lamp in each fixture and trimming down time of use to half a year. This equates to 960 kilowatt hours used in the 6-month trial. To calculate the retrofit energy use, substitute the new 29 watt lamps and 2 watt ballasts into the base equation, setting time of use to the remaining 1.5 years. This results in 1,860 kilowatt hours use for this time period. Add the two figures together to determine the total proposed energy use over the 2-year period time frame, which is 2,820 kilowatt hours. Finally, to calculate savings, we subtract the proposed situation energy use from the business as usual energy use to give us our savings of 3.9 megawatt hours over the 2 years. To continue with presentations, please select Session 1.0 Water Supply from the navigation bar. To complete the assessment for this presentation, please select Tutorial 12 Lighting Practices.